Hello everyone, I'm Zhiyuan, and today I'm going to present our final project on palette sparsification and streaming algorithms. This project is done by me and Han Sheng. So we read several papers on the topic, and many of them are quite long and sophisticated. So I decided to make this video to present the main idea and hopefully the main proof techniques in detail. Before we get started, let me give you a quick recap on list coloring. So I'm going to use an example from Chandra's first homework. In the list coloring setting, we are given a graph. Okay, so let's say this is U1 to U4. Okay, and this is V1 to V6. And every vertex has an associated list of colors. So this is LU1, this is LV1, this is LU4, and this is LV6. So in this special case, it's a bipartite graph. And every vertex has an individual list. So we can actually show that for bipartite graph, if LV for every V has size greater or equal to log of n plus 1, then the graph G is list colorable from L. By list colorable, I mean that there are no monochromatic edges, or in other words, there are no adjacent vertices with the same color. Okay, and to find the coloring, there is actually a polynomial time algorithm, polynomial time Las Vegas algorithm. Okay, for finding it. And if you forgot how to do this, as a reminder, the idea is to find a global palette. So global palette. The global palette is the union of all the colors in the graph. V in V of G, and the union of all the colors. And for every color in this global palette, we toss a coin to assign it either to the left side or the right side. So it is the palette on the left side, destroying union with the palette on the right side. And we assign it with equal probability 1/2 and 1/2. Okay, so for the coloring, if a color, um, if a for some vertex UI, if the list of UI is disjoint, it's not disjoint from the palette on the left side, then we color the vertex UI with this with this color in this intersection. And it's obvious that by coloring in this manner, there will be no conflict as the colors on the left palette are disjoint from those on the right side. If if for some vertex UI the list is destroying from the left palette, then we declare this as a failure. By standard union bound argument, we can show that with high probability, this coloring process ends in polynomial time. And we can color the right half in a similar manner, and that is pretty much the algorithm. Okay, so now let's move on to palette sparsification. In this setting, we are given a graph G. The number of vertices is n, and the maximum degree of the graph is delta. We are also given a global palette with colors from 1 to capital C. Okay, so some preliminary things about this is that we know the chromatic number chi of G is less or equal to delta plus 1. This is also called the Ising's theorem. Ising's theorem. And suppose we are given a palette from 1 to delta plus 1, we can actually color the graph by a naive greedy algorithm. There's nothing interesting about it. However, you have to go through all the edges in the graph. So okay. And for list coloring, there are individual lists, LV for every V, as we mentioned before. I'll note here that it is going to be hard for general the list coloring on general graphs. And it is also hard on specific families of graphs, even if it sounds much easier. So it's going to be hard on interval graphs. It's also hard on cographs or split graphs and bipartite graphs. However, it is solvable in polynomial time on bounded Trevis graphs. Okay. Okay, so the idea of palette sparsification is to convert a global palette into a list coloring problem where we have individual list, but the size of each individual list is much smaller than the size of the global palette. This idea and the palette sparsification theorem was proposed by Asadi, Chen, and Kana. I hope I spelled their names correctly. This was a Soda 19 paper, and it actually won the Best Paper Award. Best paper. Okay, so their theorem says that the graph G is list colorable with high probability from the list L, where each list is a sample of log n colors from the global palette with colors from 1 to delta plus 1. This is a very important theorem, and I'll illustrate it with a graph here. Okay, so suppose we are given a global palette with colors from 1 to 7, and we sample in this manner. We sample log n colors for every vertex, and construct an individual list for every vertex. Okay, suppose we did this, and I wrote it in blue color, all the sample lists that we have. Now, the very, very good thing about palette sparsification is based on this observation. For two vertices U and V, okay, so if the list of U are disjoint from the list of V, then it is impossible. To have the color of U equals the color of V. So it is impossible for there to be a conflict between U and V, which means there is no need for us to maintain the edge from between U and V. No need to maintain the edge UV. Okay, so in this example, we have some list of colors. Okay, so for example, this vertex have colors 1 to 5, and this is the drawing from 3, 7. So we know that these two vertices will never have a conflict. So we can actually remove this edge. And similarly, these two vertices have no shared colors in their list, so we can remove this edge. Okay, repeating this process, we can like remove many of these edges. So we can remove this one, and we can remove this one. We can also remove this one. Okay, as you can see here, we are given a dense graph, but after using this sampling and palette sparsification, we sparsify the graph and remove many of the edges that could never result in a conflict. So the big advantage of this palette sparsification is that we can reduce the number of relevant edges from n delta to n log square n. This is following their palette sparsification theorem, where we sample login colors from the global palette. Okay, so we have a sparser graph now, and it's near linear, which is a very huge improvement. This can give rise to improvement and applications in streaming setting, where we can have an OTUDA and space streaming algorithms for coloring from a delta plus one palette. And also we can have a OTUDA into the 3/2 algorithm, time algorithm for coloring from a delta plus one palette. These two results are from Asadi, Chen, and Kana's soda paper. Okay. So now let's move on to the paper that I want to talk about in this part of the video. The title is Palette Sparsification Beyond Delta Plus One Vertex Coloring. This paper is written by Asadi and Alon and Asadi, and it was published in Random 2020. Okay, and I want to know that Asadi actually has a YouTube video. This was like 20 minutes long, and you should definitely check it out if you're interested. And he sketched the main idea of his paper, but what I really want to do is to give you to present you the paper in greater details, and hopefully give you some more examples of this palette sparsification. So his paper consists of results in three different regimes. The first one is 1 plus epsilon delta coloring on general graphs. And the second one is delta over long delta colors on triangle-free graphs. This result was proven with a technique called Rudolph's nibble method. This is also known as semi-random method. Um, it is a very important proof technique in probabilistic methods and infograph coloring, and it's also very important for theoretical computer science. So I'm going to talk about this in the second part of the video. And for the first part of the video, I'll be focusing on this part, and this is going to be in my second part of the video. And in the following videos, I'll show you about the local version of the palette sparsification.